Hey guys, Math 6620. The data set we have here, we're going to look at mixed models. And the first video that I intend to put up is going to go through a few things we need to check to see if mixed models are even needed. There's no need diving into this world of mixed models if the standard procedures that we've learned so far are appropriate. So let's talk a little bit about the data set and what you see on the screen. The data set includes four variables: pretest, post-test, district, and instruction. And it is actually titled district instruction, and you have access to it, obviously. Um, you can see the pretest scores, post-test scores, again, district. We can come down here and see there. Now, this threw me off a little bit when I ran the summary for our data. I couldn't understand this other, so I came down and ran a table to ensure that I had uh, measurements across all 8 districts. So anyway, guys, we have a sample size of 480. These students are embedded in 8 different districts, and in each district, there are 3 different types of lecture: hybrid, lecture, or online presentation. Now, on the right side, you'll see that we have some plots, and this also will be provided to you, and you can make the changes that are appropriate for the data set that you have. Sorry, guys, I got distracted. All right, so imagine that, right? So, guys, what do we want to know here? We want to know if pre-test affects post-test. So the very first thing I would look at is I would look at a histogram of my pre-test scores. There's no reason to feel that that sample data doesn't come from a distribution, a population that has a normal distribution. I would also look at the the post-test. And again, no reason to think that that data doesn't come from a normal distribution. All right, so next thing I would want to do, I tell you what, we don't do this some, but I want to do it here. I want to to scale the predictor variable. So I'm gonna give it a mean 0, standard deviation 1. So pretest is my independent variable, and I want to set the mean to 0 and the standard deviation to 1. Now you can see if I do mean a prescaled, get a mean of 0 and a standard deviation of prescaled. I get a, I'm sorry, we get a mean of 0, standard deviation of 1. Easy for you to say, right? The reason I do that is when we start um, comparing the beta coefficients, it's just going to make it easier to compare those. All right, I think straight up, let's just create our very first model, no bells and whistles. So let's do a linear model where we take post-test, and see what happens. Well, guys, if you're like me, you probably have tunnel vision on this line right here. And what I always look at, the very first thing I look at is I look at my estimate compared to my standard error. You can see that my estimate is, well, 9.261 times higher than my standard error. So I end up with a large test statistic, which um, lends itself to a small p-value. So I have statistical significance. In other words, pre-scaled is a statistically significant predictor of post-test. We can see down here, this is another one of my go-to lines at 15% of the variance in post-test can be explained by the regression on pre-scaled. Now I can get kind of fancy here, and I've created my model, so I probably want to go examine the residuals, so I can do that very easily. And what we should see, if you look really closely, you'll see that there's a dotted line. You can barely see it. In fact, there it is. This red line should be close to that horizontal line. It's not. It deviates a little bit, but not enough to really raise concerns. Next thing I'd want to do is create the QQ plot. Remember, on our QQ plot, we want to see the points fall on the dashed diagonal line. Excellent from about right here to about right there. In the tails, we start to deviate a little bit, but I don't think it deviates enough to where I would be really concerned. Now, the next thing I'm going to look at for the model is, are our data independent? And again, think what we did. We have multiple samples from 8 districts. We also, within each district, we have 3 different instructional methods. So it's very possible that the data from each district are more similar to each other than they are from other districts. In other words, that's just a fancy way. Well, no, it's a way of saying that the measurements are correlated. So I think what I would do now is I would want to look at a box plot of my dependent variable. And I want to look at this over district. And when I do that, I get a completely different viewpoint of my data. I can see that there's something going on within these districts. For example, when I look at this, I see, if you take away, for example, D, school district D, take away those 2 measurements, the lowest value is above the median for districts A, B, and H. So there's something going on within these districts in terms of these data being correlated. And in other words, that's bad news for us because we violate our independence assumption. So guys, something is up, and I need to examine it a little bit further. So I want to go in and look at some pictures. So the first thing I want to do, I'll tell you what, first thing I need to do is access ggplot2. Guys, this is something we used back in Math 6610. So if you don't have it, just install the package and then access the library. So the first thing I want to do is I'm going to digress a little bit here and go back and make sure I've got everything titled correctly. Yeah. And just look at the relationship between pre-scale and post-test, irregardless of the district from which the measurement came from. So we have a positive relationship. We see that the coefficient is statistically significant. So that just gives us a visual of the relationship, not taking into account district or the instructional unit. Next thing I probably want to look at, this is an interesting plot. Let me make sure I've got everything correctly there. So I got pre-scaled, post-test, district. Yeah. So what I want to do here is I want to look at the same plot, but I want to look at it where the districts are colored. Now you start to get into something, don't we? We notice that there's a lot of purple, at least I do. Notice there's a lot of purple up here. I don't see any purple on the lower pre-scaled score. There's a lot of pink down here with greens and so on. So again, confirming what we saw in the box plot, the relationship between pre-scaled test, pre-test, and post-test seems to have something to do with the district from which the measurements were taken. So guys, let's, while we're at it, look at another plot. So a pre-scale, pre-test, a district, what are we doing? Okay, so we're looking at, all right, cool. So this gives us, breaks down the relationship across the 8 districts. So you can see in District A, we have a positive relationship. Not much going on in B, not much going on in C, quite a bit of variability in D. Kind of see a little negative relationship in H. So guys, there's something going on in the districts that we need to control for. So at this point of the game, what I could say is that districts vary in pretest and post-test scores, confirming to me that our observations from each district are not independent. So guys, we need some more stuff. We need a little bit more complicated model. So guys, what we could do is let's think. I'll tell you what. Let's go back to what we just did. If we wanted to, we could run 8 different models, right? And since we have 2 parameters for each model, and not even bringing in that we have 3 instructional techniques within each. So let's back up. Let's pump the brakes a little bit. We have 2 parameters, pre-test and post-test. We have 3 instructional techniques. We have 8 districts. 2 times 3 times 8 gives us 48. So we would have 48 parameter estimates, which guys would drastically increase the probability of creating a type 1 error. Not to mention that if you think what I say, 48, doing a little bit of mental arithmetic here, our sample size was 480, so 480 divided by 48. We will have a sample size of only 10 students per cell. So guys, using traditional statistical techniques, this would be problematic. Now, let's modify what we've done to include district. So I want to create a new model. I'll tell you what, let's give this model 2. So I want to predict post-test from pre-scaled, controlling for district. Now, what happens here is notice that when we control for district, that our predictor pre-scaled is no longer statistically significant. The statistical significance, in a sense, has been distributed into the districts. Now, if you notice, and if you think back when we study multiple regression, when we have categorical predictors with more than 2 groups, even with 2 groups, we create a dummy variable. And you can see the district A is missing here. So what we end up with is we end up with everything being compared to district A. For example, for district B, we can say that controlling for pre-scaled and all the other district comparisons, a 1 unit increase in pre-scaled, which is 1 standard deviation above the mean, gives us about an additional 16 points on the post-test, and it is statistically significant. In fact, all of the predictors are statistically significant. Come on down to the multiple R-squared, the adjusted R-squared. We can see that 58% of the variance in post-test is explained by the regression on district and pre-scale. But guys, I hate to break it to you, but that is not our focus here. Our focus is not whether or not, or I should say, how all of these districts compare to District A. And guys, I tell you what, this is so important. I'm going to type it out. Sometimes I know from being a student for many, many years, it's hard to write things down when spoken. So our focus is to determine whether pretest score, pre-scaled in our example, affects post-test scores when controlling for the variation coming from within the districts. So guys, that is our focus. I'll tell you what, I'm going to end this video. Next video, we're going to get into actually our first mixed effect model.